So I wanted to go over a little bit on the, oh, you have the recording on yet?
The recording is on.
Oh, it's been on. Okay.
Yes.
Yeah. So I wanted to go over a little bit of the first lecture, especially where I got stuck, which is turned out to be quite successful, fixed. Um, and so and I made some improvements here and so forth, and I will you'll have Juan will get a copy of this. You can make it available or in some way if you want. Um, there are people doing that, making talk notes available.
Yeah, we can surely find. I'm not sure what the best way to do that, but we'll find the way.
Yeah. Okay. Um, yeah, so this is what I was doing. This is I've got it a little bit more streamlined as to what's happening. So we start with RCA naught, the weakest one, and I'm not interested in giving my first talk a second time, so I just want to go through here. So this yeah, this is just the relationship between functions and sets and back that you have to make. But here is the form in which the SRM is done. So there's two. I now have two forms. One is two systems are logically equivalent, flat out, and the other is this conservativity or interpretation. So when you make the languages the same, uh, you get logical. You want logical equivalence, which is the strongest thing. And then when the languages are not, because typically you talk about a system which just has sets only, and this has much more. Then you have you have an interpretation of the big system in the little one of the strictly mathematical system into target, the target which is not strictly mathematical, which is the identity on the language of the non-mathematical part. Same if you beef this up that way. All right, so that was, and then for W, so you'll see that I do that. I set this up the same way each time. This time, if F and G don't have a common value, then some set separates them. And here, uh, logical equivalence flat out. And there's an interpretation in here of the raw WKL naught that's formulated with sets only, which is the identity on the set language. Okay, now this is the one for ACA naught. The set of all values of a given function exists. Um, and again, these are logically equivalent, and there's an interpretation. Now, if you want to do research in this area of getting better and better or different strict mathematical attacks on these more formal systems, that are not mathematical. The key thing is this really. You want to show that the system is equivalent to just pretend you've got codes all over the place and take a statement that's very mathematical like 2 and do what you want with it. You can then when you map out exactly what you want to say, you get involved in the languages. So you don't worry about the languages, just do what you want to do. Make up a statement like this, and you're fine. You can fix it up into the right kind of a conclusion. All right, and now this one was the one that I didn't say right, but it's fixed now. So for every function f, there's a largest A contained in the forward image. And that actually is the same as Pi 1 comprehension when you do codes, and then you get the conclusion we want. So this came out quite successfully. I had a couple of experts look at it, and they said that it's right. And I attached an appendix to this document. So when you see this document, you'll see a proof. You'll see a proof of this reversal. It's in there. Okay. Now, for ATR naught, I don't know how to do this without expanding the language. But since we're on the mathematical side, obviously we're going to be expanding the language. That's called doing mathematics, right? So we add the rationals in less than Q. And the statement is that given two sets of rationals, there's an order continuous embedding from one of them into the other. By order continuous, I mean 1, and preserves limits. Or if you want, just continuous in the 1, and continuous in the order topology. And that goes back to this paper in here, as I said, this one, in that volume. And then you put it in this form that you have equivalence when you make the languages the same. You actually have logical equivalence flat out. And if you don't just use ATR naught, then you're talking about an interpretation, which is the identity on the set language. Yeah, so then I say something, maybe I might have made this a little better. Something about how you introduce rationals. So we need an official SRM website, which tracks the needed extensions of the parent system, the original system for SRM. That supports SRM and tracks official strictly mathematical extensions so that all SRM reachers are on the same page. Because there could be a lot of problems because one's introducing all this, these notions, and one's introducing perhaps if we really get serious about doing this systematically, there's going to be like 500 sorts that are going to be introduced. I mean, that's the way mathematics is done, actually. And it also contains statements of SRM results with references to their proofs. We don't want to put proofs in this website. It needs to be run by a committee. When introducing the rationals, it's probably best to introduce the ordered ring of integers first and the ordered ring of rationals second, with Z and Q as separate sorts. Let's first focus on the ordered ring of integers. A lot of sorts need to be added. You have to have the ring of integers can be construed as a special case of adding a structure where the domain elements are structureless. That's very common in math. Nobody really cares what a rational really is at the at a professional level. They just have to care about that when they teach it. But they care about the structure. So the domain elements are structural as points. Whenever a structure is added, one adds a new sort for its domain. But then one also needs to add new sorts for the 1, 2, and 3 array functions from various of the sorts into various of the sorts. So when you introduce new sorts, it's not that simple. You have to link it to the old sorts in the right way. Otherwise, you can't use it. So this is an important point. That's why people don't like to use many sorted. They like to keep everything in one sort. But that's fine for normal foundations and reverse math, but not if you want to bring this strict reverse math idea to the fore. then you really have to do it much more carefully. Like, for example, you'd have to put in absolute value function from Z into omega. Things like that. And I don't believe, okay, so equality. So I recommend equality be allowed only on a given sort. This is the kind of thing the committee has to discuss. Only on a given sort, and that identity maps be used between sorts when appropriate. So for example, there's the identity map from omega into Z, right? And then there's the absolute value map the other way, right? Okay, so whether equality should be required on every single sort is not so clear. I can imagine situations where you don't want to do that, so I don't want to enforce that. The committee needs to grapple with these questions and adjust the website accordingly. So if there's a change of rules, there really has to be one place, right? You can't have the people in France doing setting it up one way, the people in Germany doing another way. You can't. I mean, the thing is just too involved to just have it without a website, I think. If we want to get a serious development of this. The SRM website should become the honest, friendly public formalization of mathematics of record. It's more honest and more friendly than what is normally done for proof assistance in the computer community. We emphasize that the site only references the literature for proofs. This is not a place where proofs are discussed. I beefed up the systems of Z2 that one should try to do an SRM treatment of. So here is a list. There are various things that are not on this list, partly because there's no SRM issue that's added. So for example, there's RCA naught plus Ramsey's theorem for pairs. That's handled by the SRM treatment of RCM naught plus the acknowledgement that Ramsey's theorem for pairs is strictly mathematical. So it doesn't have that stuff in it. So it has this stuff in it. And it's certainly not a complete list by any means. With regard to RCA naught star, these star systems, I had somewhat more a somewhat deeper discussion in this revision about this. Which I think I might want to mention about the RCA naught star. I have to find it just a second here. Yeah, program 2, program 3. Here we are. So RCA naught star is this system where you throw out sigma 1, 0, 1 induction scheme, replace it by delta 0, 0, and add exponentiation. And I notice is here. Okay, so hello. So
Hello.
And hi. So I had some more remarks about how this would link to ETF. This suggests the use of certain fragments of ETF as base theories for SRM. Perhaps the most obvious interesting idea is to simply remove the permutation axiom from ETF. So, what you might want to do and how that relates to RCA naught star is not so clear to me. In the proof in section 10 of Friedman 21, that RCA naught with functions and ETF are logically equivalent, we see 30 lemmas, the first 25 of which are proved in ETF without permutation. This suggests that ETF minus permutation has some serious legs on it. Already we see one reversal over ETFs minus perm to ETF itself, namely, to ETF itself, mentioned above, reversing minimalization or mu operator. Yeah. I mean, obviously also perm itself is reversed under ETF minus perm. I mean, it's the definition of ETF. All right. Now, ETF minus perm is quite different from RCA naught star because of the primitive recursion axiom. You still have primitive recursion in there. Instead of removing perm, we can keep perm but remove prim. And then we would look for mathematically sensitive weakenings of prim and look for implications among each other and derivations of prim all over ETF minus prim. I haven't really gone into this, but I think wanted to say some more like this. Particularly interesting here might be working with various forms of the exponentiation axiom, easily formulated strictly mathematically, and also various mathematical theorems from which we can derive exponentiation. So there is something, also just reverse ETF minus prim plus exponentiation, somewhat akin maybe to how RCA naught star works. Now, in the above discussion, we're keeping perm. We may want to go further and also drop perm. All of these ideas need to be carefully worked out. There's the overall intriguing question of whether exponentiation can be proved to be essential for a variety of theorems in countable mathematics that do not directly involve any finite counting. Obviously, if you want to count a big set, like all the functions from one finite set into itself, you're going to run into exponentiation right away. But what about just ordinary garden variety math that isn't really countable, counting centered? Can you tease out exponentiation? Can you reverse into exponentiation? I think that's kind of an interesting question. Okay, so then I had Appendix A. Yeah, I don't want to go over it, but I just want to show you it exists. There's the largest A contained in FA. This is obviously, it's obvious that the union of all these such a set. So I should say it's obvious. It's obvious from here. I mean, it's obvious that the union is going to be such a set, even without this, but you need this to argue that it is a set. That it is a set. Okay, that's comprehension. Yeah. All right, and I do this by directly constructing a function whose behavior going backwards is like an infinite path to a tree. It's behavior going backwards, meaning, you know, taking a reverse, a negative orbit, if you know what I mean. Minus omega orbit is like taking infinite paths. And it's an elementary argument like that. Okay. A couple of people who are on this site right now have looked at it. All right. So I'm going to now talk about, I'm going to give the second talk. And I got to find the, here it is. Okay, so now I'm going to do the screen share. Where do I do that? Oh, is it already screen shared? Can you see that?
No.
Okay, how do I where's the screen share selecting button? I knew I should have done it this way. Okay, so I'm in a situation here where I don't have the share screen button. I said stop share, and I wanted to restart the screen share. This must be a,
It should be on the Zoom window with all the faces.
with all the person faces.
I guess with all the names.
I got the names. Here are the names. Here they are. You're all there, and somehow I've got to find the. It's usually on the bottom somewhere, and I don't see it. It's not coming up. You think I have to get out of here and get back in?
I don't think so. It should be, there should be a green arrow, green rectangle with an arrow pointing upwards on the bottom of the screen.
Ah, yes. Yes. Now I've got to find my manuscript here. Okay, it's here. And now lecture 2. Ah, can you see it now?
Yes.
Ah, okay. I just want to fix this up so I can. Almost done. There. All right. Second lecture, which is shorter, doesn't have as much material. All right. So first talk was SRM for omega-based countable mathematics. Second talk on Z-based finite mathematics. Now, I was going to talk about SRM for real-based mathematics analysis, which is in the wilderness because we don't have a bunch of formal systems that people love for this. So Juan got me a date for a third talk a week from today. No, a week from yesterday, right?
Yes, on Thursday.
Yeah, which I'll talk on SRM for reals. Hint, reals are primitive, not defined. Okay, they get interpreted like Dedekind cuts and Cauchy sequences. All right, so this paper, this is based on this paper. This is a later paper, 2009, The Inevitability of Logical Strength, Strict Reverse Math, Logic Colloquium 06. Okay, and this is the agenda. And there's this philosophical point that's very important. And this philosophical point can only be done with SRM. So there's a big foundational point. Is there a way of formalizing mathematics that avoids logical strength and Gödel phenomena generally? Maybe entirely. That's what I meant. It's a radical thing. Where the consistency problem essentially disappears. Perhaps the logician's way of formalizing math is overkill with its overly general principles, especially infamous logical schemes, and all of this can be avoided. If we just formalize more economically, we can outright prove consistency. A lot of FOM worries are gone. To a large extent, this is already refuted by SRM and ETF as discussed in the first lecture. However, one can still blame logical strength on that being infinitary mathematics. So maybe the point is we shouldn't be doing any infinitary mathematics. I'm playing devil's advocate here. So it is important to refute this for finite mathematics. Actually, there's a grain of truth in this gross anti-foundationalism. RCF, real closed fields, that is, the first order theory, and ACF, algebraically closed fields, formalize very significant portions of mathematics, avoiding Gödel phenomena. And I gave a consistency proof of RCF and ACF and EFA and showed, I forgot the dates on it, darn it. It's not recent, and showed that they were interpretable in Q. The Q result was also published by Ferrara with his own different techniques. All right, not at all clear how far one can take this. Perhaps the whole of mathematics that isn't somehow combinatorial in nature, but rather algebraic or geometric, can be proved consistent in weak systems, or perhaps not, shown by spectacular reversals. All right. Formalization, sugared predicate calculus. Okay, when we go into formalizing mathematics, we encounter things that are banned from ordinary predicate calculus. And for most logical investigations, we don't really care. Specifically, we need for real formalization, we need many sorts, undefined terms, function and relation variables. This is important. And relativized quantifiers. These are the biggies, and there are more minor things like writing, I'm writing for all x comma y, that F is supposed to be a universal quantifier, for all x comma y and so forth. This is a whole area of sugared predicate calculus. This won't be really important for this lecture, although it will be clear that the need for this arises in full formalizations. We will ignore what we should be in free many-sorted logic with function and relation variables until this becomes important in section 4. Okay, I'm speaking out of both sides of my mouth. This is just not important, really. It's just obvious that certain things that I formalize are obviously I want some of these features when you actually make the formalization. All right, the system Q. So let's, one thing I do need in the background, the system Q, which already consists of strictly mathematical theorems, will play a role in the discussion here. The signature of Q, as you all well know, is 0s plus times less than equals. You can do Q without less than, because it actually is just a definition. Yeah, so Q has the non-logical axioms, as you know. Raphael Robinson's. All right, now SRM for, okay, now SRM for true ... Let ... be a subsequence of the list of 5 symbols, 0 successor, plus, less than, and equals. I'm talking about linear mathematics where everything is decidable and really cool. Okay, that's what this is about. In other words, no multiplication at the moment. Just to make this systematic. This is a system consisting of all true sentences in the first order language with signature ... inside here. There's 32 such systems, right? 2 to the 5th is 32. Each true ... is, of course, very decidable by elimination of quantifiers due to Pressburger. If true ... is finally axiomatizable, we look for a logically equivalent theory consisting entirely of strictly mathematical theorems. The rest are not finally axiomatizable, and we cannot find a finitely many strictly mathematical statements, right? It's not possible that are equivalent to it because it's not finally axiomatized, but we want to expand the language. So this is just the SRM discipline in a very a low-level setup where everything is where you have quantifier elimination. Okay, what can be required? T consists entirely of finitely many strictly mathematical theorems, of course. The language being extended by this theory, and every sentence in this theory provable in T is provable in, no, it's just conservative extension. We're not in general going to, we're going to discuss whether we can get more. It's not clear what more we can get in this kind of setup, like interpretation. I believe you can't get that when it's infinitely axiomatized, but there's some issues. Now let's look at finally axiomatizability of the 32 signatures. That's only some of them. If we include plus, then because of the congruence axioms, it's not finally axiomatized, no matter what else you have. It's not, if you have plus and any of the other possible 16 possibilities, it's not going to be finally axiomatized. So we just need to look at subsequences of 0s less than equals. I mean, for this case, when we have plus, the presence of 0 makes no difference. So we need only look at subsequences of s less than equals. Yeah. In other words, I'm talking about the case where we're finally axiomatized. Or whatever. Okay. Yeah. Okay. So if we just have the empty set, it's obviously finally axiomatized. If you just have S, it's not finally axiomatized. If you just have less than, it's finally axiomatized. Equal, yes. S and less than, yes. S and 0, no. Less than equals, yes. S less than equals, yes. Okay. And each of these 12 cases, the finite axiomatization that comes to mind is already entirely composed of strictly mathematical theorems in the first place. So you have the best possible situation. The cases below remain with non-finitely axiomatized, and that's when we have this S and 0s and S equals and 0s equals and plus together with any of the 16. For the 4 in here, we can add less than to the language and get T composed of finitely many strictly mathematical theorems, where T proves true, and every sentence in the language provable in T is provable in true. Consensitivity. However, we don't get an interpretation of T in true. Can we have such a T with an interpretation of T in true, which is the identity on the language? I haven't had a chance to think this through. You may want to think about that. For 3, down here, up here. For 3, we also need to expand the language because it's not finally axiomatized. So we let's work with the whole thing. We choose T to be where we just add multiplication. And the axioms equality, axioms for 0s less than equals, division by each standard integer with remainder less than n, where n is external. This is pretty familiar to you. You have to, all this junk has to be put in, but then the red meat is in here. Quotient remainder theorem for a quotient that's a standard integer. And we get that T consists entirely of finitely many mathematical theorems. T proves this, and every consequence of T in here is a consequence of here. No, it's conservative extension. We can ask more of T. We won't have an interpretation, and it's unclear whether T is decidable. Whether we haven't looked carefully at the other ones when you don't have everything. So this is different, of course, than the main points I want to make, at the higher level. But this is already pretty, I think, pretty cute stuff. And there may be some things that require some thought, some real thought. I'm not sure. Okay, SRM for PFA. So PFA is I like this terminology. This is polynomial function arithmetic. It's also called bounded arithmetic. It's also called I sigma zero. And it's actually also sometimes called I delta zero, same thing. And its signature is 0s plus times less than and equals. And we have the usual definition of the sigma zero formulas. These are the formulas with bounded quantifiers. And the axioms of this system are Q and the induction scheme for sigma zero formulas. So obviously you want to do some SRM work on this because this is illegal in strict reverse math, right? Okay, our beloved schemes. All right, so we follow the SRM treatment of PFA in Friedman 09. And this is actually quite meaty. This is a serious matter. With some simplifications that rely on the familiarity of coding in the literature of folklore. Namely, we convert this paper, I did it very comprehensive and complicated. It may be hard to follow that paper, but I think I'm streamlining it, simplifying it a little bit for this lecture. So the first step is to convert PFA with omega, of course, the semi-ring, to PFA with a ring, Z. Once you do that, that simplifies matters considerably. So the idea is the first thing to do is just shift PFA with omega to PFA with Z, the ring. And that's no big deal. Remember, we're still going to have schemes. It's still going to be a logic theory. But you can do some nice things. The fact that it's Z, you can play around a little bit. All right. So from the literature and folklore, we know how to use Z in addition to omega, in fact, in PFA, because of familiar coding. So anyways, we write this as PFA of Z. And the signature is 0Z, 1Z, plus Z, times Z, and less than Z. And that's going to be the target for the SRM. Now, we'll also be able to obviously go back to the original PFA, but this will clarify the work, what I had to do. All right, so by the way, we have no idea how to give a strictly mathematical equivalent of PFA Z, keeping the same language. But we expand. I did succeed in expanding this nicely in two different ways. One way is to add a second sort for finite. So in both cases, I add sorts. If I want to stay in sort Z, I don't know how to do strict reverse math here. It's like saying I want to do strict reverse math in the language of Z2. I have no idea. All right. One way is to add a second sort for finite subsets of Z together with epsilon relation. We view this thing as in sort. Why did I say this? Sort Z. Here we have a second sort, fin of Z, right? Fin of Z meaning the finite subsets of Z. This system is written FSTZ, finite sets with Z. Finite sets with Z for finite set theory over Z. The signature is Z fin Z, it's two sorted with 0, 1, plus, times, less than epsilon. And what are the axioms? What are the non-logical axioms of this? Linearly ordered integral domain axioms for Z. Z is a linearly ordered integral domain, as you know. Finite interval, in other words, the closed interval from X to Y exists as a set. The Boolean difference, if I have A and B, A / B exists. Set addition, A plus B exists. You can add two sets. Set multiplication exists. You can perform A times B. And the least element principle, every non-empty set has the least element. This is my SRM attack on PFA of Z. Okay. We'll talk about the results. Okay. By the way, I think these were typos. In some places, I wrote the weaker linearly ordered commutative ring axiom instead of linearly ordered integral domain axiom. I'm pretty sure I meant the latter. This creeped in because of some revisions. But also it may not make any difference. Yeah, it's a little annoying that we have that, but it's under control. All right, so the theorem is there's an interpretation of this system I just described into PFAZ, which is the identity on the language of the target. Just the kind of stuff we want. Okay. In particular, of course, FSTZ proves all of PFAZ, and that's highly non-trivial. So I spent a lot of, there's a pretty long proof in there of that. All right, we can adhere to PFA instead of PFAZ by using the obvious form of FSTZ that incorporates omega, which I could write this way. That's one way to one way to adhere to PFA, which is based on omega. But I can't just, I need Z. Omega is not enough. You really need this as a group. Marine. Yeah. This is only a semi-ring. All right, there's an interpretation of FSTZ of omega into PFA, which is the identity on L of PFA. Actually, this is a mistake. Probably I want this. Probably say that. Yeah. I mean, that's also a good system when you put both in. It's also good. Okay, I have a second way of doing this SRM treatment of PFA. I have a second way. And that is to use finite sequences. And both of these things have their advantages. It uses finite sequences of integers, not finite sets. And then we have the ring operations, less than, length of a. So you need more primitives, though, when you do this. We have the concept of the length of a sequence. And that's, that's an element of omega. That's an integer. And that's fine, because we already have integers. I mean, we're doing integers anyway. All right, length of a sequence. The ith term of a sequence, so, alpha, written alpha at I. In other words, so-called, application of the sequence, alpha at I. And that returns an integer. Remember, this is only finite sequence of integers. We don't have finite sequences of finite sequences of integers. That's a whole nother subject that come up at the end, near the end of the talk. That's a whole nother matter. We're just talking about, I don't want to make this, I want to make this system have the smallest signature. I don't want big signatures, but I have to have some meaty signatures. All right. So in the case of finite sequences of Z, here's what the signature looks like. We have length and value, as I said, and then all the other expected stuff. Two sorted. The non-logical axioms of this, what does this look like? Linearly ordered integral domain axioms. All lengths are greater than or equal to zero. You don't want any negative lengths, right? But you do want the empty sequence. A val makes sense. Okay. You see that arrows that goes down? Actually, that was taken from the wrong font. It should be thicker. That arrows that goes down is part of what's called free logic. It means it denotes. So you see, I'm going to use, it's not too important, you know, you can follow, but I'm just saying that that's the way I do, the way it should be done. All right, the value of alpha n exists, makes sense if and only if n is between 1 and the length of alpha. Makes sense, right? The finite sequence 0 through n exists. Now, you know how to formalize that. It asks for something such that the ith term is I plus 1, or, you know, whatever. The length is n plus 1. All right, length of A equals length of B implies minus A alpha plus beta, alpha times beta exists. Now, I decided that I didn't add these as primitives, minus, plus, and times on finite sequences, but you could. In fact, you would when that committee on SRM is formed and everybody wants to do everything completely. Of course, you're gonna put that in. But this would be just formalized. This would just be formalized in the obvious way that there exists a finite sequence which does what it's supposed to. Okay. Now we don't want to put concatenation either in the language because I want to keep this minimal. Although one would obviously these are pieces of material for the committee. The concatenation is just defined to be a sequence whose length is the sum of the two lengths and whose values at places are just obviously where they have to be. And now this one is really heavy. Given an integer n, internal integer n, I can take any finite sequence and concatenate it n times. Alpha, 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 dot, 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 n times. And I claim that exists. Now, how do I say that that exists? I have to say that there's a beta such that the values of beta are correct, right? You know, you have to use a little bit of arithmetic there to know what I'm talking about, right? A residue there, right? Okay. Now, and then finally, this one is also pretty heavy. There's a finite sequence enumerating the terms of alpha that are not terms of beta. And by enumerating, I don't necessarily mean in strict order less than, although I could have said that. It's weaker. There's a finite sequence whose terms are exactly the terms of alpha that are not terms of beta. And every non-empty finite sequence has a least term. Okay. This is the system. This is obviously, this is all strictly mathematical. I mean, you could make a fuss that that's pretty mathematical. I mean, I might find it hard to come up with a place in the literature that looks exactly like that, but probably I can make it look quite close to that. So you know, this is probably fine. Now you could ask questions about whether you can get rid of that or replace it with something else that's even finer, you know, whatever. That's SRM work. All right. There's an interpretation of FSQZ into PFAZ, which is the identity on the language of the target, which is just exactly what we want. And I said I said the same thing about FSTZ. Both of them have this this property. We can adhere to PFA rather than PFAZ by using obvious form of FSQZ QZ that incorporates omega. And you have to add this because you have to keep this. Okay, there's an interpretation of FSQZ of omega into PFA, which is the identity on L of PFA. That isn't right, is it? There isn't such a thing. This is nonsensical construction. Yeah, there we are. All right. Now let's graduate. Okay, I so far don't have any logical strength. Remember, I was going to prove that logical strength exists. Remember, in finite mathematics, I don't have any logical strength in PFA, but I do have logical strength in EFA. And my personal opinion is that the first non-problematically, the weakest non-problematic case of having logical strength is EFA. All right. Now, EFA is defined to be exponential function arithmetic, which is I sigma naught of X. Let's see if we can get this back up here. Okay, and the signature is 0s plus times exponentiation less than and equals with a single sort omega. The intended interpretation has exponentiation of n to the 0 is 1. Yeah. By the way, the reason I mention that is because 0 to the 0 is 1 has been decided somehow to be 1. I think that that's correct. That's the best choice. All right. So the sigma 0 exp formulas are defined like this, as you'd expect. And the non-logical axioms of EFA are Q, the defining axioms for exponentiation, the induction scheme for sigma 0x. All right? And we treat EFA by extending, so we're going to do an SRM treatment of EFA by extending FSTZ and FSQZ as follows. This is the first one. This is the easy one. We're just going to add the axiom common multiple. For every n greater than 0, the integers from 1 through n have a common multiple. And there's an interpretation of FSTZ plus common multiple into EFA, which is the identity on L of PFA. I didn't say it was the identity on L of EFA. I said on L of PFA. And the same is true of FSQZ. So this is a weaker result. Where I'm not saying that FSTZ plus CM proves EFA. Now, why doesn't it prove EFA? It actually does prove EFA. Okay, there's another version of EFA which doesn't have exponentiation as a primitive. If you look at Hayek-Pudlak, they do that, for example. It's a complicated statement that every number has an exponent. It's a complicated statement. You have to state it in a complicated way. It's a long-winded thing. It's ugly. But it's fine. I didn't address this here. There's more to address than I can talk on. So this, but the official EFA has exponentiation added as function symbols. This is the difference. So obviously this isn't going to prove EFA, but you're going to be able to interpret EFA in here. You see. All right, but this does show, this theorem is strong enough to show the inevitability of logical strength, right? Because FSTZ is unabashedly reverse strictly mathematical, and CM is certainly strictly mathematical. Do you want to, okay, I think I was careful about this in the paper, but they obviously have a multiple, namely zero. So how about a common non-zero multiple? Let's try that. Let's try to actually stay awake. Here we are. All right. Note that theorem 5.1 is not as strong as expected. We're not saying that we prove this, but it does show the inevitability. Now, to get the stronger SRM for EFA, let's start over with FSTZ and FSQZ. We expand both these languages to include the binary map in EFA and extend FSTZ by the strictly mathematical defining axioms for X from EFA. And we write these as, we do this on both sides, FSTZ plus exp and FXQZ plus exp. We certainly do not have FSTZ plus exp and FXQZ plus exp proves EFA. The problem is that the binary exponential function has not been internalized into FSTZ and FSQZ. It's not been internalized. You see, when I had functions and sets in the first lecture with ETF and RCA naught, I needed an axiom that each talk about the other in a serious way. The sets and functions talk to each other. So here, I haven't done this yet. We need to prove that the graph of the binary exponential function up to R, in other words, cutoff. The graph, remember, this is finite mathematics. We have to cut everything off. The binary x function up to R exists as a set in FSTZ and strictly enumerated in FSQZ. We need to do that. Now, we can't just do that by using the word, just use the word internalized. We have to actually state what we're going to do. Now, this is handled, if we were only dealing with binary exponentiation, this is clearer. This is clearer. For binary base 2 exponentiation. Base 2 exponentiation, this whole business is clearer, but it can be done for binary exponentiation. So with both FSTZ and FSQZ, we add 2 to the 0 is 1, 2 to the n plus 1 is 2 times 2 to the n. And then for FSTZ, we further add that the set of all 2 to the m such that m is less than n exists as a set. That is what's called internalization, except that I'm not internalizing the graph, which is what I really want to internalize. I'm just internalizing something that I can state strictly mathematically, namely the range. I'm just saying that the range is a set is really the simplest way to talk about internalization. But you got to prove that that actually does get you somehow the graph, and that's not so trivial, but it's intuitively clear. Now for FSQZ, we further add that the finite sequence 2 to the 1 ... 2 to the n exists. FSTZ knows that there's exactly one set that looks like this. There's exactly one set that looks like this. And therefore, this must be it. Then we get the graph that we want. This is a little bit of a subtle argument. A similar argument also works for FSQZ, that there's exactly one finite sequence that looks like this. and therefore this must be that one. Then we also get the graph that we want. All right, this is all a little subtle. All right, fortunately, this kind of argument can be carried out with some care to handle EFA with its binary exponentiation, binary. We again start with FSTZ and FSQZ, and this time we add the defining equations for exp to both. But we want to further add internalization, that the set of all x and m less than r exists. And for fs, so I'm claiming that with a subtle argument, you can show that this axiom does the trick, that axiom serves as the internalization axiom. And so we get strictly mathematical extensions of FSTZ and FSQZ, which are themselves fine, with an interpretation into EFA, which is identity on the full language. Okay. Now, one step higher, what about CIFA? CIFA is super exponentiation, is the super exponential function arithmetic. That's what CIFA is. I sigma naught of super exp. Its language is based on this, and the intended interpretation has this by yeah. That's the right way to do it. All right, now sigma 0 super exp is defined as you might expect, just the usual thing. And the non-logical axioms are EFA together with the defining equations for super exp, right? And then the induction, where it's a sigma 0 formula. So this is all expected. This system is already in the literature. I think this is also handled in Hayek-Putlock, I think. Yeah. So we treat CIFA by extending FSTZ as follows. Add exp and super exp to the language, add the defining axioms for these, and then add the limited ranges of exp and the limited ranges of super exp as sets. Limited meaning this is finite mathematics. In other words, those are the internalization axioms. Also, the analogous addition for FSQZ side, on that side, which is the enumerators, the enumeration sequences. Then we get strictly mathematical extensions of CIFA with interpretations into CIFA that are the identity on the language of CIFA. All right, now, fine. I'm getting close to the end of the talk. I think this is the last item. How do I get strength, more strength? Well, I take the gloves off a little bit, and what I do is I add to FSTZ and FSQZ, I introduce finite binary relations on Z and finite sequences of finite binary relations on Z. And I gotta add all the, those are sorts, and I gotta add all the material to make that make sense, to make that work. And we introduce finite rooted trees whose vertices are in Z as certain binary relations on Z. Also introduce the cardinality of finite rooted trees whose vertices are in Z. Then introduce inf-preserving embeddings from one finite rooted tree in Z into another, and then state my finite form of Kruskal's theorem. This results in a strict mathematical theory in Z-based finite mathematics of high strength or interpretation power. This is high strength or interpretation power. It's not that kind of strong stuff where I have something like this, interpretations with the identity on stuff. So this is very high strength, this is beyond, this is. Okay, what is it? Pi 1-2 bar and Pi 1-2 TI or something. Yeah, I mean, this is the level of crustless there. All right, I think that's all I want to say today.